The next topic, converting a continuous time system to an equivalent discrete time system. There are 5 available methods: impulse invariant, step response invariance, backward difference, bilinear Z transform, and matched Z transform. Only BZT, bilinear Z transform, is useful and can be used in serious and practical applications. The rest have some problems. You're going to be familiar with what's going on. Anyhow, converting a continuous time system to an equivalent discrete time system, impulse invariant method, the first one. Here you see the block diagram of the system. H continuous of t is multiplied by impulse train, leading to hp of t, then impulse train conversion into discrete time. Here you'll get hd discrete of n, which is equal to hc of n times ts, sampling time. T stands for sampling time, which is equal to 1 over fs, sampling frequency. Okay? Now, the above figure illustrates how to convert a continuous time system to an equivalent discrete time one using impulse invariant method. A continuous time system is transformed into discrete time in such a way that the impulse response of the discrete time system is equal to the impulse response of the continuous time system that has been uniformly sampled. That's the idea. Using this method is only possible in cases where the frequency response of the system is completely or at least almost band limited. Okay? So, a constraint for using. By having the continuous time impulse response, h continuous of t, and multiplying it by the impulse train is obtained, hp of t is obtained, and then by converting it to hd of n, the discrete time impulse response is calculated. Now, here we have shown the idea in mathematics. hp of t will be equal to summation hc of n times ts or t times multiplied by delta of t minus nts. Here you see the frequency response. hp of j omega will be equal to hc of nts times e to the power of minus j omega nts. And in discrete configuration, hd of omega or e to the power of j omega, both are the same, is equal to summation, just leave it, hd of, just compare them by i's, hd of n times e to the power of minus j omega n. Okay? Here just notice that what omega is equal to omega times omega s. Now, hd of n is equal to hc of nts. hd of omega is equal to hp of j omega over ts, or similar idea for the last line in equation. Now, what's the mapping? Consider the mapping from analog to digital domain. It's very important. hp of s is equal to Laplace transform of summation hc nt times delta of t minus nts, which will lead to sigma n from minus up to plus infinity hc of nts times Laplace of delta t and shifted versions. Okay? Because hc of nts is a constant. So you can move Laplace transform from here up to here. Very simply. Now, you know that the Laplace transform of delta t is 1. Delta t of t minus 1 ts is 1 times e to the power of minus s times 1t, and n will be n times what we just mentioned. Now, having this equation from here, what do we have in digital environment? hd of z, definitely z transform is equal to summation hd of n times z to the power of minus n. Now substitution, which will be equal to, just notice, hd hc nts z to the power of minus n. So it shows that hd of z is equal to hp of s when z is equal to e to the power of s times ts. So you've got mapping here. Write it down and notice what's the problem with it. We are going to sort it out. Therefore, the mapping s to z is being equal to e to the power of s times t is used for this transformation, this mapping. Now, the problem with this method is revealed here. The left side of the vertical axis in the continuous time system is mapped into the unit circle. For example, if you take S0 to be equal to minus 0.5, you'll get Z0 will be equal to e to the power of minus 0.5 times t. Definitely, its amplitude or apse of Z0 is less than 1, meaning that inside unit circle. So, left part of S domain up to here, left part of S domain will be mapped to inside unit circle in Z domain. That's very good. Stable system will be mapped into stable system in digital counterpart. What about the right side? It's okay as well. The right side of the vertical axis in the continuous time system is mapped to outside the unit circle. For example, if you take S0 to be equal to 0.5, it will lead to Z0 being equal to e to the power of 0.5 times t. Definitely, absolute value of Z0 is greater than 1. Now, these two properties up to here are very good so far, meaning that analog stable system, you just remember it from Laplace transform definition, analog stable system maps to digital stable system and unstable to unstable. Okay? But the main drawback is that the vertical distance from minus pi over ts up to plus pi over ts on the vertical axis of the analog system, when you are going to analyze the frequency response, you take S, which is equal to sigma plus j omega, and putting sigma being equal to 0, so in vertical axis, you can analyze frequency response of Laplace transform. Okay? Just a memorandum from systems, signals and systems you had in BSc. Anyhow, on the vertical axis of the analog system is mapped to the entire unit circle. That's the problem. So, very limited frequency band will be mapped to all parts in digital environment. What about the frequencies higher than what we just mentioned here? There will be an ambiguity. Which frequency is equal to what you get in the digital environment? You cannot judge. So there is ambiguity. Anyhow, S0 being at the origin will be mapped to Z0 being equal to 1. The degree is 0, locating at unit circle. S0 being equal to minus J pi over Ts will lead to Z0 being equal to minus 1, a complete rotation on the circle. So frequency response has reached to end in digital environment. Now, S0 being equal to J times pi over Ts, you'll have Z0 being equal to minus 1 again. Rotation from lower pi unit circle, upper part. Okay? Now, as a result, if the desired frequency is outside this range, there will be ambiguity. This ambiguity is called folding. Here you see a very useful illustration. You see here, left part of S plane is mapped inside unit circle. Very good. Stable system will be mapped into stable system in Z plane. An unstable system, right side of J omega axis in S plane, will be mapped to outside parts of unit circle. So unstable system will be unstable in Z plane. The major drawback is here again. Just moving from lower frequency 0 up to pi over T will lead to moving from 0 frequency up to max frequency here. Or similarly, if you get this part, you see here the indicator, moving from 0 up to minus pi over T, you will have a movement from here up to 180 degree, the maximum frequency allowed in Z plane. So what about this part? You will have again a rotation, a rotation, a rotation. So which frequency has caused you to be here in a specific frequency? You don't know. So if the frequency is very band limited around the origin, it's a good technique. Otherwise, you cannot use it in serious applications. So that's why we mentioned that this method is useless. Anyhow, if Hc of t contains delta of t, this method will have problems. This method is not applicable for high-pass and band-stop filters since they have polynomials of the same degree in the numerator and denominator of their transfer function, which leads to the appearance of the impulse in their impulse response. This mapping is not conformal, and only poles and not zeros are mapped according to what we just mentioned as a mapping. Okay? So another restriction. Now, as an example, transform the normalized filter h of s being equal to 1 over s plus 1. You should rapidly compute in your brain what's the angular cutoff frequency here. You just notice that it's 1 radian per second. Okay? Here you see what we just mentioned. Omega c is equal to 1 radian per second into an equivalent digital system using the impulse invariance method. These are digital cutoff frequency is equal to 20 hertz and the sampling frequency is 200 hertz. Now solution. Very simple mathematics using z being equal to e to the power of s times t. So we'll have omega being equal to omega times ts. Cutoff frequency is omega c over t, which will be 4t times pi. Okay? That is, the digital and analog cutoff frequencies are the same. Then h of s assume with cutoff frequency 1 W convert to radian second into the following form so that its cutoff frequency is the same as omega c. Here you see the transfer function in Laplace domain. Okay, for t times pi over s plus 4t times pi. Now, impulse invariant method is applied. Okay, what about time domain? Here you see h of t will be equal to omega c times e to the power of minus omega c t times u of t. Okay, right hand sided signal. Now, h of n will be omega c e to the power of minus omega c and replacement. T is equal to n ts, okay? And u of t will be u of n. Now, you can write z transform because it's h of n. So h of z will be equal to omega c over 1 minus e to the power of minus omega c times t times z minus 1. And the last line, you just see every details here. Okay, now, converting a continuous time system to an equivalent discrete time system, this time using step response invariance method. It's again useless. Why? Because this method is very similar to the impulse invariant method. That suffices. Okay? Anyhow, but we want to continue the discussion. With the difference that in this method, the step response of the analog system must be found before converting to the z domain. For this, the impulse response of the analog system h of s must be multiplied by the Laplace transform of step, that is 1 over s. You just remember, integration or step is equivalent to 1 over s. What about derivative? It will be s times everything. Anyhow, g of s is equal to h of s times 1 over s because we are going to use step response. So that's the difference. Then the step response in the time domain is obtained using the inverse of the Laplace transform as follows. Very simply, you just write g of t will be equal to Laplace inverse of gs. Then the following conversion is considered to convert the analog signal to digital, again t being equal to n times ts. After this step, the z transform of the above relation is written, okay? H of z times 1 over 1 minus z minus 1. So the difference here appears compared to the previous method. Considering that the z transform of the digital step is equal to 1 over 1 minus z to the power of minus 1, as a result, h of z becomes equal to, h of z will be equal to g of z times 1 minus z minus 1. That's it. This method has the same drawbacks as the impulse invariance method, so in practice you cannot use it. Anyhow, the next example. I just leave it for you yourself to read it out. When it's useless, why should we waste time for it? But you see here the complete details of computation. Very interesting mathematics, but we will leave it for you as self-study. Now, backward difference method. What does it mean? A differential equation is obtained for the discrete time system by replacing the derivatives of the differential equation of the continuous time system with backward differences. This method is usually used in the digital simulation of the analog systems. The motivation for its use is that it is obvious that the derivative of a continuous function in time can be approximated by the difference of its successive examples. Okay, in mathematics, the idea is very simple. dy of t over dt plus a times y of t being equal to x of t, a normal differential equation. So h continuous of s, Laplace transform for the system will be y of s over x of s will be equal to 1 over s plus a. Now, in digital form, dy of t over dt will be equal to y of n minus y of n minus 1 over t. Okay? Again, repeating the idea, dy of t over dt will be equal to the difference between two adjacent samples in output over the time we have used sampling time, plus y of t, y of n being equal to x of t, x of n. Of course, t should converge to 0 to have a better approximation. Okay? Now, hd of z, hd of z will be equal to y of z over x of z, which will be equal to 1 over 1 minus z to the power of minus 1 over t plus a. So with this method, the mapping is this time s being equal to 1 minus z minus 1 over t. Now, in general, s to the power of l will be equal to 1 minus z to the power of minus 1 to the power of l over t to the power of l. Now, s being equal to 1 minus z minus 1 over t, you'll have z being equal to 1 over 1 minus st. So, assuming that s times t is equal to sigma plus j omega, a complex number, you will have abs of z being equal to 1 over square root of 1 minus sigma to the power of 2 plus omega to the power of 2. Now, if sigma is less than 0, left part, then abs of z is less than 1. It seems completely normal and good. That is, the left poles of the S-plane are mapped into the unit circle in the Z-plane. But if you take S be equal to j omega, Z will be equal to 1 over 1 minus j omega times t, or 1 over 2 times 1 plus j omega t over 1 minus j omega t, leading to the last line. So z will be equal to r times e to the power of j omega will be equal to 0.5 times 1 plus e to the power of j times 2 times arctangent of omega ts. Now, for omega moving from minus infinity up to plus infinity, it will be r being equal to 0.5, a radius of a 0.5, consider it, and theta will move from 0 up to 2 pi. What does it mean? Okay, here you see the idea. First, showing the red part, stable system will be mapped to inside unit circle, but not covering all parts. That's the first drawback. We expected to have all parts of the unit circle inside to be covered, but very limited area is covered. And the rest, unstable system, will be even inside the unit circle and of course outside the unit circle. So the second problem, of course, completely related to the major idea. And what about analyzing frequency response? Just consider green line moving from frequency being equal to 0 up to infinity plus infinity. We will have a movement from here 0 degree and on the unit circle, but we expect the movement in frequency analysis to be on the unit circle, but you'll move over or on another circle. So only this very limited part is acceptable. You see here the location of two circles. Only this part is legit. Otherwise, you are not moving inside legit area to analyze and speak about frequency response. And this technique is too much worse than the first one. Okay? So that figure shows a backward difference mapping. The problem with this method is obvious. Only for very small values of omega times ts, that is, when the desired frequency of omega is much smaller than the sampling rate of fs or 1 over ts, apse of z is located near the unit circle. Therefore, if h of j omega is essentially band limited, we can choose t so small that h desired or h discrete of e to the power of j omega approximates the values of h continuous of j omega around the desired frequency. In short, although in the backward difference transformation, the problem of folding, which is mentioned in the impulse invariance method, is avoided, but this method has its own problems, as mentioned, especially that the j omega axis, apart from a small region around z being equal to 1, is not mapped onto the unit circle, even approximately. So, as shown in figure 7.10, the left side of the vertical axis of the S-plane is mapped into a circle with center 0.5 and radius of 0.5 in the plane Z, that is the left side of the unit circle in Z-plane, doesn't belong to the stable region. Can you accept it? The meaning of this word is that it's not possible to design a high-pass filter wherein the poles are on the left side of and inside the unit circle in the Z-plane. With this method is rarely used in practice. Similarly, you may have forward difference. What does it mean? Again, a similar differential equation, this time having yn plus 1 minus yn over t. instead of writing yn minus yn minus 1, this time we are looking at forward difference. The previous one was backward difference. This one is forward difference. This method is not causal, of course. And it's also possible to define central difference. You see here, n plus 1 minus n minus 1, leaving y of n apart. So definitely the distance is 2. We should have 2 here. Okay? Again, repeating y of n plus 1 minus y of n minus 1 over t times 2. T time 2 times t. Sorry. Now, using the best method, BZT, bilinear Z transform, we often need to design digital filters that have the same useful characteristics as an analog filter. The most effective method is to have a mapping from the domain of S to Z so that it preserves the important characteristics of the domain response of the analog filter transfer function. The most common mapping is called BZT and is defined as follows. Please write it down. S being equal to K times Z minus 1 over Z plus 1, where K is equal to 1 or 2 over Ts, or 2 times Fs. That's the best method. With BZT, the stable region in the S-plane is mapped to a stable region in the Z-plane. Also, the unstable region in the S-plane is mapped to an unstable region in the Z-plane. Here you see an example. S is equal to sigma plus j times 0, and sigma if is equal less than 0, so the absolute value of z will be less than 1, and if this sigma is greater than 0, the abs of z will be greater than 1. So far so good. The j omega axis in the S-plane is mapped to the unit circle in the Z-plane. How? Just consider S being equal to j omega because you are mentioning frequency response, so sigma should be equal to 0. From S part will be equal to k times 1 minus e to the power of minus j omega over 1 plus e to the power of minus j omega. Just having k times j sine of omega over 2 over divided by cosine of omega over 2, leading to having a tangent. Okay, j times k times tan of omega over 2, tangent. Now, so to be precise, omega will be equal to k times tangent of omega over 2. Apart from the declared problem, nonlinear relation of omega with capital Omega with omega, this transformation has no other problems, and that one can also be easily solved. The most important characteristic of this mapping is that it's conformal now this time, which means that the shape of the domain of the frequency response, for example, passband, repel, stopband, attenuation, blah blah, doesn't change. The second effect is that the frequency response becomes warped. This effect is in the form that the response of the digital filter at a frequency omega is mapped to the response of the analog filter at the frequency of capital Omega, not having a linear relation, having a tangent form. Okay? It means a little bit problem but we are going to sort it out very easily. Don't worry. It means that the range of the analog filter, that's omega, is from minus infinity up to plus infinity, definitely. While it's omega from minus pi up to pi for digital filter. Note that when omega, capital Omega, approaches to minus infinity, omega will approach to minus p. That's our morality. Very good. Also, we will have omega approaching to plus infinity. Equivalently, we will have omega being approaching to plus pi. Of course, minus pi and plus pi both are the same point, 180 degree on the unit circle. Now, for small values of omega, there is a linear relation between omega and capital Omega. But for large values, the relation is nonlinear, having the form of tangent, as we mentioned, which leads to a distortion or warping in the frequency response of digital filter. This effect can be compensated by pre-warping the analog filter before applying BZT. Also, as mentioned before, BZT maps the left region of the S-plane into the unit circle in the Z domain. This ensures that analog stable filters are converted to digital stable ones, and figure 7.11 shows BZT mapping. Now this time everything is pretty good. Left side being mapped into inside unit circle. So stable system will be mapped into stable system. What about the right side? Just white part will be mapped to outside the unit circle. And what about here? When you move around the vertical axis from frequency 0 being here up to plus infinity, so moving from here up to 180 degree. And the blue sign shows the reverse movement, so the reverse movement also in the Z plane. And that's the miracle of BZT. Now, just modeling what we mentioned. Example 7.7. Assuming that TS is equal to 1 or having a 1000 hertz or 1k hertz as sampling frequency, millisecond, and FC being equal to 50 hertz, design a digital low-pass filter from an analog prototype of the form Butterworth of degree 1, h of s being equal to 1 over s plus 1, using this time BZT method. No solution. Cutoff in analog will be pi over 10, which means here you see pi over 10 having capital omega c, or cutoff in analog domain will be somehow different from 50 hertz declared in digital environment. Instead, you'll have a tangent relation leading to 50.4153 hertz. So if you take 50 hertz as cutoff in analog environment, the design will lead to another cutoff in digital environment, because 50 hertz in digital environment needs having 50.4153 hertz in analog. Okay? Why? Because of this relation we mentioned. That's the key point. Now, the cutoff frequency h of j omega is equal to 1 radian per second. So its value should be changed to omega c denormalized. Therefore, instead of using h of s, the following relationship should be used. H of s needs to be equal to 1 over s over omega c plus 1. This filter have a cutoff frequency of omega c radian per second, not 1 radian per second, because we need it. So the prototype needs to be converted to whatever we need. Then, instead of S, put its equivalent in terms of BZT mapping. Now, very simple replacement. H of Z will be equal to 1 over, we had S. So, substitution, K times 1 minus Z to the power of minus 1 over 1 plus Z minus 1 over omega C plus 1. That's it. Which will lead to 0.1367 plus 0.1367 z minus 1 over 1 minus 0.7265 z minus 1. The following code simulates the above computations in Python. We will run the program inside PyCharm. Let's run it. Okay. Here you see the result. Okay. Just notice 250 hertz as being cut off. Okay. 1 over square root of 2, which is rather 0.771. Okay. So the result is completely acceptable. What we have written as code, we just show it here. The readability here is better than inside PyCharm because of the font. Anyhow, cut off the same strategy, we mentioned it earlier. Stop band the same. Okay. Now, declaration. FC 50 Hertz, sampling frequency 1000. N of FFT the same as regular, the definition we just had it so far. Omega C, capital Omega C, how it's calculated. Now, num and denom, you see here, num 1, denom 1 over omega C. Now, num z, denom z, signal bilinear num and denom and fs, and the rest is very simple. Okay? Now, take home. Write a program in Python that converts previous analog filter design using Butterworth, Chebyshev, and elliptic to digital equivalent using BZT. Okay? We learn about Butterworth, Chebyshev 1, Chebyshev 2, and elliptic. Now, that's the time to use them in digital environment, of course, using BZT. That's the idea. Now, matched Z-transform method as the last method for converting analog to digital. This method converts the poles and zeros of the analog filter where the numerator and denominator of the function are factored as terms of the first or second order directly into the poles and zeros of the equivalent digital filter. For impulse invariant method, we had h of s being equal to 1 over s plus alpha. Of course, ROC demands that real part of s being greater than minus 1. So h of t will be equal to e to the power of minus alpha times t multiplied by u of t, a causal system, a right-hand-sided system. So h of n will be equal to e to the power of minus alpha times t times n multiplied by u of n, and h of z, we just had all parts earlier mentioned, everything, okay? So for the impulse invariance method, we can consider the mapping as, we just mentioned it again. Here you see the results. Okay. Now, S plus alpha, we will have z minus e to the power of minus alpha times t over z, or equivalently 1 minus e to the power of minus alpha times t times z minus 1. In matched z transform method, this mapping is used to convert the numerator and denominator of the factorized analog transfer function into the digital domain. Here you see the main equation. I don't want to read it out because this method is useless. Just having a simple primary idea about what the definition is. Okay? Now, for a pair of complex roots, the above mapping is simplified as what you see here. And it should be noted that in the impulse invariance method, only the poles are mapped with the mentioned method, and the zeros of the two systems are different. But meanwhile, in the match Z transform, not only the poles but also the zeros are mapped as follows. Okay? This method also has the same problems mentioned for the impulse invariant method, folding and inappropriateness in the form of high pass and band pass. So, a useless method. Now, example. Assuming t being equal to 0.1 s second and omega c being equal to 2 radian per second, design a digital low pass filter from an analog prototype of the form h of s being equal to 1 over s over omega c plus 1 using match z transform. Here you see what we need to write, okay? With a gain equal to 1 at zero frequency, the value of k is equal to 0.1813. Eventually, h of z will be equal to 0.1813 over 1 minus 0.8131 z minus 1.